So good morning. Today I'll try to talk about a little bit about van der Waals heterostructures. To start, I will say an heterostructure is normally a combination of two or more materials that interface each other. As you can see in the figure, it's an example of some. Eu não perguntei, vocês estão me ouvindo bem?
Perfeito.
Sim, tranquilo.
Show. As you can see in the figure, it's just an example of some heterostructure. They usually grown with epitaxy, like a molecular beam or chemical vapor deposition. Lattice mismatch can be a problem in such structures. So when you grow them, you have to be careful about sizes, so you don't have a string interfering in the material and creating so much defects. But obviously the growth methods are well developed, so we grow materials with little small defects. They can be used normally as electronic devices, solar cells also. They also can be characterized by their band offset. We have normally three types of heterostructures. In the first type, they can be used as laser applications. Type 2 can be used in solar cells. And type 3 can be used as tunneling field effect transistor. So we can have layered materials. Actually, layer materials are formed by atomic layers with strong in-plane bonds, but between the layers we have weak van der Waals interaction. So after graphene was firstly obtained, another materials were also exfoliated to single or a few atomic layers. Here I have disclaimed, I put here the slide as layered materials. Silicene and germanium, for example, in the upper right part of the figure, are not layered materials, but you can grow a few layers or even a single layer of them. So why talk about layered materials when I was talking about heterostructures? Now that you have this kind of material, you can stack them and form a heterostructure. That's why we call them van der Waals heterostructure. So you don't need to grow one of the other. You simply start to put one over the other. So with this, you can see in the figure, as I was saying, now that we have some few layers or one atomic layer, we can stack them together. Instead of growing the surfaces, we now can peel them off from one material and put in the top of another, and then we have as we can see in the C part of the figure, we can have really well-defined layers with almost no defects, because you almost don't have defects when you do this transfer. The problem is you don't have scalability. When you do epitaxy, you grow like wafer size materials, and with this stacking method, we're still progressing, so you don't have big devices. So with this, we have like a Lego style of materials, and you don't have to worry too much about lattice match, because the layers will interact quickly, and so it will not change the bonds. Here, as an example, we have a graphene layer between two hexagonal boron nitride layers, and between them we have a molybdenum disulfide layer. This is a red light emitting diode obtained using van der Waals heterostructures. So we have a lot of possible application as devices. They can be ultra low power devices. They can be also flexible, transparent, and also ultra thin. Besides the applications of devices, we also have interesting phenomena. Like here in the left side of the figure, we have graphene, a layer of graphene rotated over a boron nitride layer. They form like moire patterns. If you look in the internet, you have really beautiful images. And in the right part, we have a Hofstadter butterfly. The Hofstadter butterfly, it's in a fractal energy spectrum that only appear when you have certain periodic potential and a strong magnetic field. That can be obtained with graphene rotated over boron nitride. So you have also new phenomena to look up. Hofstadter predicted this in 1976, but just now it can be accessed experimentally. They also now this year, it's a new production. You have also 1D van der Waals heterostructures. This one consists of a carbon nanotube at the center. In the middle, you have a boron nitride nanotube, and outmost nanotube is a molybdenum disulfide. This was obtained experimentally this year. So my presentation is really short. It shows a really oversimplified view of the field, and so thank you very much.
Thank you. Exatamente 8 minutos. Perguntas?